differentiating a function once, but then differentiating that derivative once or even more than once. This is the idea of what we call the second or third derivatives. And we'll have a look a wee bit later on about why these are important to go maybe third or fourth. But what we're going to look at first of all is the idea of a second derivative. So if we have a function f of x, the first derivative would be regarded as f dash or f prime x, and the second derivative would be f double prime x or f double dash x, second derivative. And that's the derivative of our first derivative. And why would you want to know that? What information does it give us? Well, first thing, it helps to think about the idea of the rate of change of the rate of change. You can get your head around that. In some aspects, each of these quantities has a value in itself. For instance, when we're looking at the idea of motion in the movement of an object, we can think about the idea of having a function of displacement or distance. If we differentiate that, the rate of change of displacement is velocity. So if our function here was about displacement, then our derivative would be a function of velocity, the rate of change that object is moving a distance. However, if we differentiate that again, the rate of change of velocity, we actually call acceleration. That's the rate of change of the velocity of an object. So in this regard, the second derivative is a very valuable and a recognized quantity. So when you're working on these kind of ideas, you're going to be often finding the second derivative of a function. The second thing, and the thing we're going to concentrate on just now, is the idea of using the second derivative to determine the nature of stationary points on a graph. You may have up to now used a table of values in order to prove that a stationary point is a maximum or a minimum. And what we're going to look at is a different way of determining that. We're going to do that using first of all, to demonstrate that with some graphs. So the first thing we're going to do is we're going to use Desmos to create this function here. It's a cubic function, the green curve, and it has two stationary points. It has one maximum stationary point and one minimum stationary point. What I want to do is to introduce into the graph the derivative function of that, or the derivative value. If you've in the past been asked to draw the derivative of a function, you may have done it on a separate graph, perhaps underneath. But what you would have done is recognize the fact that we know that the value of the gradient at these 2 points is 0. So you would have marked 0 on the x-axis at those 2 points, and then you would have tried to work out if the graph is above or below the x-axis at these points, and it would give you a quadratic function. That's the graph of f dash x, or the derivative of the original function. In other words, that purple graph, each of the values there is actually the gradient of the green curve at any particular point. So for instance, if we were to take the value of the function here, when y is 10, y is 10 appears roughly when x is about negative 3.2. What's the actual value of the gradient at that point? The gradient of the curve, oh, I'm actually reading, let's help if I actually read the right, I'm doing it the wrong way around. Okay, so let's have a look at, for instance, this point here on the green curve. Thank you very much. So we're talking about 4 and a bit, okay? If we want to find out what the gradient is, well, we can match it up with the corresponding value here. and it tells us that the gradient of the curve there is roughly nearly 12. Okay, so the gradient of the curve here is approximately 12 because the purple curve tells us that. Okay, so well, that's something that's fairly straightforward. So if I just make the original function disappear, that's our derivative, and we can do the same thing again. What does the gradient of that look like if we found if so we differentiate that, and then we get this. Again, we know that at the turning point of this one here, the gradient is 0. And to the left of the turning point, the gradient's negative, and to the right, the gradient's positive. So we have this orange curve, which represents the second derivative of the original function. So let's get rid of the first derivative and reintroduce the original curve. What's the connection between the two? Well, the important connection here is as follows. At the point where we've got a maximum turning point, and we look at the corresponding value of our second derivative, you'll notice that it is below the x-axis. In other words, it has a negative value. And if you look at the second turning point, here it's a minimum turning point, and the corresponding value on the second derivative is above the x-axis. In other words, it's positive. So when we have a maximum turning point, the second derivative is negative, and when we have a minimum turning point, the second derivative is positive. Coincidence? Well, no, because I'll show you another one. Here's another cubic function. It has, again, a minimum and a maximum in the other order. Very quickly, I'll show you the first derivative. Again, it's a parabola, and the derivative of that, again, in this case, is a straight line. If we get rid of the first one and we have a look to see, does that property work again? Here's our minimum turning point. Here's the x-axis. You'll notice that at a minimum turning point, the second derivative has a positive value. It's even gone off the board here. And at the second point, the maximum turning point, the second derivative is way down here, negative. So again, second derivative is negative, corresponds to a maximum turning point. Second derivative is positive, corresponds to a minimum turning point. Okay, we're going to go back to the first one and try and explain why. See if I can do it justice. What's happening here around this maximum turning point is that the gradient is changing, obviously. Okay, so the gradient value, we know the gradient value here is 0. And we know that just to the right of it, that's a negative gradient, which is kind of 0 point, say -1, and then it gets steeper. So that would be -2, and then it gets steeper, still -3 somewhere. And if you look to the left of it, the gradient was something at one point like 1, and then here it's getting steeper, so that's 2, steeper here, 3. So as the value of x increases along here, you'll notice that the value of the gradient is decreasing. In other words, the rate of change of the gradient is going down the way, it's decreasing. And because the gradient is the first derivative, the rate of change of the gradient represents the second derivative. In other words, that rate of change is negative. And if we have a look at the minimum turning point, again we know that the gradient right at that turning point is 0. To the left of it, the gradient was negative, and then increasing negative, -2, at another point -3, and to the right of the turning point, the gradient starts to become positive and larger. So as x is increasing here, you'll notice that the values of the gradient are increasing, they're becoming more positive. In other words, the rate of change is a positive value. A rate of change of gradient is the second derivative. So if the second derivative is positive, it means that the gradient is changing from a negative to a positive, which back on our table of values was again the evidence we were looking for. Negative, 0, positive would have been, oops, if I get that right, it would have been our illustration of negative, 0, positive. There's our minimum turning point. So that's hopefully an explanation of why the second derivative helps us to predict the nature of the turning point. And if you have a look at here, I'll just summarize it on this table. For any function f of x, for any particular value, if the second derivative is negative, then f of x has a maximum stationary value. If the second derivative is positive, the function has a minimum stationary value, and if the second derivative is 0, well, that's the one we'll have to have a look at. It may have a point of inflection, but we have to check that with a table of signs. There's now and again there's a few kind of issues with being confident about that. Quite often it's a point of inflection, but not always. But the main thing we're going to take from this is we're looking particularly for the second derivative to be either negative or positive, and we can be sure that that's actually either maximum or minimum. Okay, so a bit of a long explanation. I hope that's okay. Oops, let's go forward from here. So let's have a look at this. Example 16, investigate the nature of the stationary points of this function. So rather than using a table of values, we're going to find the second derivative. So for a given function f of x, the second derivative, the first derivative, sorry, is going to be 3x squared plus 2 times 1.5 is 3x, and then we've got minus 6. Second derivative, which will look f double prime x, you just differentiate again, 2 times 3 is 6x, plus, and 3x differentiates to 3, and that's our second derivative function. But we've got two functions there. We don't know yet what to put in for x because we don't know the actual coordinates of the stationary points. So we have to dial back and we have to discover where these are, and we can say that stationary points exist when f prime x equals 0, or dy by dx, f dash x equals 0, something that we can state to say these are when they exist. So going back to our first derivative, we can say, i.e. 3x squared plus 3x minus 6 equals 0. We can take, factorize that with a common factor of 3 first of all. Which we can then divide through, or we can divide through by 3 to leave us just with x squared plus x minus 2 equals 0. That simplifies it. We don't have, we're going to have a trinomial factor here, x plus 2, I guess at x minus 1, which means that either x plus 2 equals 0 or x minus 1 equals 0. So our solutions are x equals negative 2 and x equals 1. So stationary points at x equals negative 2 and x equals 1. So we've now got two bits of information that we can put together. We have values for x when stationary points occur, and we have a second derivative which is going to be our tester. So what was it? F of x equals 6x plus 3. So the first stationary point occurs when x equals negative 2. So we're looking for f double prime of negative 2. Substitute negative 2 in here. And we get negative 12 plus 3 is negative 9. So the value of the second derivative when x is negative 2 is negative 9. What does that mean? That is a negative value. Which implies, if that's negative, it's a maximum turning point. At x equals 1, we're looking to substitute in 1 into our second derivative, which gives us 9, which happens, of course, to be a positive value. The actual numeric value doesn't matter. It's the whether it's positive or negative at the moment. And if it's a second derivative is positive, then it's a minimum turning point. So we've got a maximum turning point when x equals 2, minimum turning point when x equals 1. What does the question ask? Investigate the nature of the stationary points. We could find the y coordinates to actually find the full coordinates of it, but I'm not going to bother at this stage. It's been long enough. So we can summarize it by saying that we have a maximum turning point at x equals negative 2, and we've got a minimum turning point at x equals 1. Okay, that's how we use the second derivative to determine the nature of the stationary points of functions that we have. Okay, I hope that that's made sense. You can scroll back and certainly try some examples yourself.